A bunch of years in academia, spent a bunch of years working at Microsoft, and talk about what I think is something that we often don't talk about when we talk about technology and its history, and that actually is the fact that often the non-technical factors have more to do with success than the technical ones do. And so I want to say a little bit about that. But before I do that, let's see if this actually works. Which one of these is the remote? Clearly not this one. So, you know, I thought I would sort of start and point out a few bits of history and think about what was not true that long ago. Not that long ago, Hormel wasn't really worrying about protecting the trademark on Spam. You know, that just wasn't an issue. Fishing was mostly stuff I did with my grandfather. We've had a lot of phrases enter the popular vernacular that weren't true that long ago. For many of us, it wasn't that long ago. The hi-fi was a much more popular concept than Wi-Fi. And it wasn't that long ago that books didn't need batteries. And it wasn't that long ago that a friend was someone you presumably actually knew. So a lot of things have changed, and so it's worthwhile, I thought, on the opportunity of Purdue's 50th to sort of look back a little bit and think about what was true 50 years ago. So I'm going to go back even further than Doug and put a few things in context. But before I do that, I just wanted to show a photo. So I was a Purdue grad student during most of the era that Doug was talking about, and when he was talking about where in the hierarchy assistant professors sat, remember grad students are below that in the hierarchy. And so this is a tongue-in-jest picture taken, one of several, of me in Peter Denning's house. And we posed various pictures of us cleaning dishes and vacuuming and washing the car and the like. And we had a good time in the process. But there were lots of things that Dave Schrader and Doug's comments brought back as fun memories. As Doug was talking about sharing terminals with the graduate students, I did remember that there was a priority faculty terminal in later years. So there was some pecking order. So I want to just sort of summarize some of the things to think about. So let's start with politics and think about what was true in 1962 and how much has changed. The Civil Rights Act was still 2 years away, and Ole Miss had just been forcibly integrated. And so there have been some profound social changes. That was the year of the Cuban Missile Crisis. I'm just barely old enough to remember that. I remember that because they took all the cartoons off TV that week. That's what I remember about the Cuban Missile Crisis. You know, this was also the 50th anniversary of the Beatles' first hit. It's the year that Wilt Chamberlain scored 100 points. And where I'm living now, it was the inauguration of the Seattle World's Fair with Space Needle and the monorail. Lots of things have changed. On the economic front, you know, Walmart, Kmart opened their first stores. It's a picture of Sam Walton's first 5 and dime there. The Dow Jones average closed for the year at 652. Of course, average income was about $5,000, and I went and I looked for Purdue's tuition, and I couldn't find it, but I think most all of the Big Ten tuition was about the same. For the year, just under $300. And some of us are old enough to remember gas wars. Gas was about $28.9 at the time. And I remember when I went up to 40 cents, I thought that was outrageous. And on the science and technology front, by '62, most of the US population had a television, but almost all of them were black and white. In fact, some of us remember the NBC Peacock and the fact that at the start of a program it would say, "This program is brought to you in living color," because that was a big deal. It was also the year of the first live transatlantic satellite broadcast, something we take for granted as well. Transcontinental or transatlantic jet service was just a few years old. The Concorde was on the drawing boards. John Glenn just orbited the Earth as the first American to do so. And Watson and Crick received the Nobel Prize for discovering the structure of DNA. On the computing front, and there's some examples of this upstairs, that picture in the upper right there is a 2 megabyte removable disk pack, right? That was enterprise quality secondary storage. Space War appeared at MIT, so video games made an early appearance. There's a PDP-1 there on the second picture from the top on the right. And something that I cut my teeth on in computing, the teletype model ASR-33. And if you've ever used an ASR-33, the primary repair tools are an oil can and a wrench. And typing on one then will definitely build forearm strength because the keys are like using a hammer to press down. IBM mainframes, which now seem ancient, had not yet appeared. The CDC 6600 was about to appear, and as was mentioned earlier, there were a couple dual 6500s here and the 6600. Those were state-of-the-art at the time that the department was created. And the ARPANET, the beginnings of internet working, was still multiple years away. It was a very, very different time. Lots has changed in 50 years. And yet what I would say is that one of the things I've come to believe is that all those years that I was a professor and students always asked for copies of old exams, one of the things that I would perpetually say, certainly in the technology business, is happy to give you copies of the old exams. But bear in mind, the questions may not change, but the answers do. Because they really do change. Because what changes what's appropriate is the ratio of capabilities, cost, performance, capacities. And when those change, you get different answers. Because after all, a smartphone is really no different than those mainframes that I had on the picture before. It's just a matter of capacity, cost, and performance. But when those things change, you get new kinds of answers. But I do fundamentally believe that this is important to keep in mind. I've used this slide in talks in various incarnations for most of the last 20 years. There are really only 3 questions in this life, and everything else is a subset special case. There's life in the universe, matter, structures. There's biology and its processes. And there are the things that relate to the human condition. Everything is a variation on those things in some way. Computing is interesting because it impinges on almost all of those things in interesting ways. And I've been fortunate to spend a big chunk of my career in high-performance computing getting to play amateur scientist in biology and medicine, in physics and engineering, and even working with people in computing and the social sciences. And that's been a great deal of fun. One of the things that I think is a big challenge for us going forward as we think about the future of computing and research universities in the 21st century is in the university world, we typically reward specialization. In fact, we increasingly reward hyper-specialization. The old joke that you learn more and more about less and less until you know everything about nothing, and then we give you a PhD. Not without some truth. And yet most of the interesting problems lie at the intersection of our definitions of traditional disciplines. And so one of our big challenges, I think, in society at large is how we facilitate dialogue across disciplines, because we're often separated by a language that's incompatible. And as I said, many of the problems are in fact the same. And that's what I want to sort of talk a little bit about in the few minutes today. But as I said, and this is an observation that the late Jim Gray made, fundamentally, if we look back 50 years, what's changed are these things: the speed and capacity of networking, the speed and capacity of computing, the speed and capacity of storage, and the cost of those things. because there really isn't any difference between a smartphone and a supercomputer. Nor is there much difference in the user interface of a smartphone and what happened 40 years into basic research at Xerox PARC. Our mechanism for interacting with computers fundamentally hasn't changed in most of the last 40 years. I think there's some opportunities for that to change in some interesting ways. But these ratios are important, and that's why I keep saying the questions don't change, but the answers really do as you look back and you look forward. So I want to talk a little bit about the future and what I think are some of the social and technical challenges, but let me make a couple of social observations first. Because if we look back 50 years and you ask yourself what the future will be at some point in looking forward, it's hard to say, and at some point it really becomes science fiction, and anybody's guess is as good as anybody else's. But what I've generally observed is that if you look in the technology world, it's often the case that the people outside a discipline are better predictors than the people inside. Because we tend to see the warts and the limitations of the technology, and we lock in tunnel vision on some of the things that it can do. Bringing people in from outside often gives a different perspective on things, and you get some different kinds of ideas. And of course, inventing the future is by far the easiest thing to do, rather than talking about it. But that, of course, is also, even in its simplest, a very, very difficult thing to do. So I don't expect you to read this quote, but it's a prescient observation. Licklider was one of the early leaders of DARPA and was, by most measures, one of the intellectual founders of what became the ARPANET, and notwithstanding what Vint Cerf and others did, because Lick was the one who put the money behind making the project happen. And if you look at what this says, and note the date, 1960, so over 50 years ago, he envisioned a world where a network set of computers could provide shared access to information over high-speed communication lines. Pretty much like the web. A 50-plus-year-old vision of what could be. Now you have to think about what was true at that time. What he's talking about was connecting a national and international network of machines, as Doug said earlier, each of which cost millions of dollars, when high-speed networking here meant 56 kb leased telecom lines. That was the state of the art. That's a pretty big leap in terms of orders of magnitude change. And so being able to suspend disbelief and question some of those assumptions is one of the things that lets new things happen. And I was privileged to be at Illinois when NCSO Mosaic appeared. You know, really what began the web browser revolution. I was probably, I don't know if I was in the first 10 people to see it after the prototype was running, but probably pretty close to it. And I had a couple reactions to that as a geek. One was this was pretty cool, right? The fact that you could look at pictures from places around the world. The other was, as someone who'd been using the ARPANET and the internet for years, was there was nothing I could do with Mosaic that I couldn't do with anonymous FTP. One of my friends said that's true, but there's a whole lot of people who can't spell anonymous. And in fact, I dare say more computing people than would like to admit learned how to spell the word anonymous so they could use FTP. So there are some lessons from history there about the past and some reflections on the future. The other thing that I think is true is that the language we use shapes a lot of context about how we think about things. Now the linguists have a phrase for this, the Sapir-Whorf hypothesis, and it's been hotly debated in linguistic circles about its validity, but fundamentally it says the words you use shape how you think about things. And whether it's true in linguistic circles or not, I absolutely believe it's true in computing. The tools and technologies that you have available shape the kind of things you think about doing. And if you look at the history of computing, Doug talked about how the VAX really changed computing research, and it did, not just here, but nationally and internationally. And you can go on down the hierarchy and think about those things that happened when the PCs and webs appeared, when smartphones have appeared, and the big things that are happening now around cloud computing and mobile and embedded devices. The technology does shape the kind of things we think about. I think the innovations occur not only when those technologies are available, but when you can step back and say, what could be in the future that isn't true now? Because if you can do that, you get a head start on the future. You make some bets on some of the things that could be. And this is the thing, if you hear nothing else I say today, remember this. These two things are the same. The markup on one is substantial. The presentation matters. It really does. And here's why it matters in a technical context. What I used to tell my grad students for years, and I fundamentally believe, is in the competition for ideas, and it relates to what the previous speaker just said, in the competition for ideas, who tells the best story wins. Because there are more good ideas always than there are resources. And if you can tell a good story, you'll be successful. And so I think as we think about science and engineering education, that's one of the things to keep in mind, that the ability to communicate your ideas effectively is key to success in the real world. It's actually key to success in writing a successful research proposal, and Lord knows students think it's important that professors be able to communicate. I actually have a story about wine and exams as well that happened to me here. When I was a graduate teaching assistant, I was teaching a class and the final exam met on Saturday night before Christmas. Now, the fact that that's when the exam is enough by itself to tell you that I was a graduate student. I didn't want to be there, none of the students wanted to be there, but this was when the exam was. So I show up on Saturday night with a pile of exams, and the students assemble, they spread out across the classroom to create some air gap. One kid shows up in a tuxedo, sits down at the desk, pulls a white cloth out of his tuxedo pocket, spreads it out on the adjoining desk, pulls a bottle of wine out, opens it with a corkscrew, produces a glass, sets it on the white cloth. I pass out the exams. He pours himself a glass, raises it in salute, starts the exam. I know he had more fun than I did. So if you think sort of about that history, here are a few ways to sort of track it. You know, if you correlate our history of computing with bad science fiction movies, you go look at those old 1950s movies that had computers in them, they're all about flashing lights. And later on, you get spinning tape drives as the icon of movies. And eventually you get, well, you get boxes. We had flashing lights for a while in the 70s and 80s in the days of SGI. Computers don't look that interesting anymore as props in movies. But I do want to talk about some of the things that I think may be true in the future. And I mentioned one of them a second ago. Whether you're a fan of Macs or of Android or of iOS or Windows, all of those interfaces are the same. Now, they differ in lots of ways, and there's huge market competition, but they all derive from seminal work that was done at Xerox PARC in the 70s around windows, icons, menus, and pointers. And they're all variations on that theme. And essentially, all of our computing devices are passive. They literally do nothing unless we poke them, by and large. We're right on the point where some of those transitions in scale and capacity and cost mean that we can begin to think about computing being an assistant rather than us being the one who has to drive the activity. So as we think about the future of natural interaction with speech and gesture and emotional context, as Dave was talking about, learning systems, we're on the edge of an interesting transition. What's made it happen is computing has become cheap enough that we can think about optimizing it for us rather than forcing us to adapt to its idiosyncrasies. And that's a big potential change. There are lots of technical things which I think in the interest of time I won't talk about. I do want to hit on a couple though. And that is over the last 40 or 50 years, we've been the beneficiary of an amazing exponential. what's been called in the popular press Moore's Law. Now, this is the original 1965 paper that Gordon Moore wrote with this highly technical title, Cramming More Components onto Integrated Circuits. And this was a trade press article. It wasn't a research article. But if you think about what's happened over that past 40 or 50 years, we've seen a doubling of performance roughly every 18 months. And that's been because the size of transistors that we can pack onto chips has also shrunk on that same scaling. It's not a law. It's a whole lot of engineering activity and a whole lot of financial investment. When I left Purdue, we had just started to teach Introduction to VLSI Design with this iconic Mead and Conway textbook. The tools we used in class to draw research integrated circuits were colored pencils and graph paper. Right? You could actually do something interesting and do it that way and draw it on a CalComp pen plotter. It's another ancient technology some of you younger may have never seen. We've seen orders of magnitude change. At the time that happened, the cost of building a semiconductor fab line was a few $1 million. It's approaching $10 billion now for a single fabrication facility. It's questionable whether anyone on the planet can afford to spend $100 billion to build a fabrication facility. It's also true that the number of atoms, in terms of the thickness of a transistor, is down to count them on one hand almost. We're approaching some interesting quantum mechanical limits. We're also approaching some interesting economic limits. So there's change afoot in this space in terms of what it means for computer architecture and in terms of what it means for the future of computing design. One of the things that's happening is this, and this is one of those interplays between technology, sociology, and economics. Most of the computing industry, and this is one of the lessons from my time at Microsoft, has been successful because it has embraced probably the one idea that computer science has given the world, and that's abstraction. The old joke in computing, there's no problem that can't be solved with another level of indirection. It's also not without some truth. We've separated applications and systems and architecture and algorithms and hardware. Those things are blurring in some really interesting way. If you look at all that's happening in terms of suits and countersuits around IP, if you look at what's happening about investments, we're seeing a collision of cultures, a collision of the people historically in computing, the people historically in communications, and the people historically in content. And everybody who's at the bottom of that stack is trying to climb up. And everybody who's at the top is trying to climb down because they realize they need integrated capabilities. And that's driving a huge set of changes, but it's bringing some conflicting cultures together in some complex and really interesting ways that it'll be curious to see what emerges over the next few years. One of the reasons I went to Microsoft was to try to apply a lot of the lessons I'd learned in high-performance computing to the design of cloud data centers. And they actually are mostly twins separated at birth. So I was talking about science fiction movies before. If I ask you what a computer center looks like today, this is probably your iconic image. You know, a bunch of black boxes sitting on some raised floor with fluorescent lights. First job I had working at a computer center, I was still an undergraduate. I was living in an unair-conditioned apartment. It was about 105 in the summer. My office was actually in the computer room. It was about 65 in there. So every day I had about a 50-degree thermal shock when I went to work. And so I wore a coat at work, and then I wore shorts at home. That was sort of the compromise. But this is what we normally think of. And in fact, if you look at what's behind this, this is what you get. You get electrical substations, you get chilling towers, you get control systems, you get lead-acid battery backups, you get diesel generators, you get rectifiers, you get chilling towers, and water cooling. Turned out for a long time before the economic downturn, most of the limitation of building out the massive infrastructure that supports social networking and web search, one of the big limiters was a worldwide shortage of diesel generators. There were bidding wars for priority to acquire those. The big data center requires a bunch of them to provide backup power. Let me sort of put this in perspective for you. This is a picture of one Microsoft data center, and it's true if you want to talk about Google or Facebook or anybody else. One of those data centers is 10 to 20 times the size of the football field up the road in terms of footprint. Draws anywhere from 50 to 75 megawatts of power. Any one of those things, it'll have several 100,000 computers in it. Any one of those things is bigger than the entire internet was just a few years ago. So there's been a lot of work on thinking about how to optimize the design of these, reliability, energy efficiency. And the 50 to 75 megawatts is mostly bounded not by technology and not even by money, because one of these costs about $500 million each. And everybody who's in this space is building worldwide networks of them. The major limitation is that somewhere around 75 megawatts, if you want to go above that, you actually have to be a utility. And the computing folks don't want to be in the business of owning nuclear power plants, not too surprisingly. So energy efficiency is a big challenge at scale. And there are a bunch of issues around that. Here's another example of technology culture collision. And I spent a lot of time on this problem over the last couple years. Anybody who's ever pulled out their smartphone and swore and cursed when they lost a call or couldn't get a data connection will understand what I'm about to say. I was talking about the fact that our user interface hasn't changed much in the last 40 years. The way we manage wireless spectrum hasn't changed since Marconi thought wireless was really cool. This is an example of the US spectrum allocation. I'm just about finished. The marching band's going to come any minute. It's salami sliced and allocated for dedicated purposes because at the time this was done, state-of-the-art radio technology was vacuum tube based, and designing any transceiver to operate required you to specify a band and design the hardware for it. That's no longer true. We've got enough computing power now that we can do a lot of what used to be done in hardware and software. That's what so-called software-defined radio actually is. Here's one of the ugly truths. Every one of those times that you see the battles to acquire spectrum for a wireless carrier, and they're huge and intense, remember that most wireless spectrum, most places, most of the time, is actually unused. If you were to turn on a spectrum analyzer in this room and look, that's what you'd find. And it's true almost any place in the planet. Sort of to give you an analogy, think about having bought a car, and at the time you took title from it from the dealer, what came with the car was a license to drive only in lane number 3. Didn't matter what else was going on in the road. You hope there actually is a lane number 3. Sometimes there isn't. That's all you can do. What we actually do, of course, is we dynamically adapt. And that's really what the future has to be, because we can't make more spectrum. That's a physical law. Now, the other thing about traffic you ought to bear in mind, as someone who spent a lot of time around the world, is there are two worldviews on traffic. There are the places like the US where the number of lanes is an integer. There are other parts of the world where it's a real number. And Lord help you if you confuse those two, because it's an interesting thing. Here's another way to think about some of these exponentials and rate of increase. I talked about those 2 megabyte disk packs earlier. A megabyte's about the amount of text in a paperback book that we all read on an airplane. 3 orders of magnitude more, a gigabyte's about what on a DVD, all right, that you'd watch a movie on. A terabyte, another 3 orders of magnitude, you're talking about 1 million books. Now think about the fact that you can buy that for sub $100 now. You can essentially put the entire text of the Library of Congress in any kid's hands. There are huge opportunities there. If you go up another 3 orders of magnitude to a petabyte, That's about all the content of academic library holdings on the planet. And any one of us has enough money to buy that kind of storage. That's a profound change. You go up another 3 orders of magnitude, 5 exabytes, it's about the number of words spoken in the entire history of humanity. Those exponentials really matter, and they've changed what's possible. Here's one way to think about the effect of that. Anyone who's gone online and used a translator from one language to another with text, it's gotten enormously better over the last decade. You might ask yourself why. We've had increased understanding of human linguistics, but in point of fact, that has almost none of the effect. Almost all the reason that it's gotten better, and mind you, I still wouldn't want to negotiate a peace treaty with the quality of translation, but if you don't read kanji, it'll at least get you the gist of the text. The reason it's got so much better is because we have text at a scale that we've never had before. Statistics is your friend at that scale. You actually do gain insights at scale, because if you have millions of comparisons of something, they actually are statistically valid. There are lots of other things I could say about the effects of this. I'll leave you with sort of one last thing to think about in terms of its impact on science. One of the things that has happened, if we look back at the history of science, is that we have mostly lived in a world of scarcity. Think about the scientific process that we were lied to about in primary school. You know, theory, hypothesis, experiment. None of that's true, all right? It's a lie we propagate because science, like everything else, is a hugely, intensely competitive endeavor with rivalries and competitions and all kinds of things that happen. We rationalize what happens after the fact because most of the time we're pursuing hunches and then we justify it with some rigor afterward. That's the real truth. Don't let anybody tell you otherwise. But the reason why we've historically done experiments is to get data, because we didn't have any. Data was rare, scarce, and expensive. For the first time in human history, that actually is not true anymore. Data is neither rare, nor scarce, nor expensive. It's ubiquitous, it's overwhelming, and it's cheap. And so we've had a psychological shift to, I need to conduct an experiment to get some data, to in many domains, I'm drowning in data. The question is, what interesting questions can I ask from that data? And that's a big change. It's challenging a lot of the sociology of science. And so, should we stop and wait for the band?
We're going to take a break and watch the band play. They're going to march by the front of the building. They're going to stop and play Hail Purdue for all of you.
Greg, you really don't want me to sing. Can't sing, can't dance. So I think the last thing standing between you and a break, so I will try to be mercifully brief. There are just a couple other things I wanted to say about big data and culture and some of the challenges that I think we face. I was talking about this comment that Herb Simon made years ago, the late Herb Simon, that one thing that a plethora of information creates is a poverty of attention. And when you have enormous amounts of data, the challenge becomes how do you extract insights from that data? And that's a big social change that we now face in ways that we haven't before. And there are lots of ways to think about it. There is a whole cadre of astronomers, for example, who never go to telescopes. They simply analyze data from whole sky surveys. And that's increasingly a phenomenon that's challenging and changing a lot of the ways that science is practiced. And here's a way that you might not think about that. And I certainly lived through my own version of this at time as I built up unique research infrastructure. I had a conversation once after I was a full professor with a young assistant professor in a related domain to the one in which I was working. And I said, what are you thinking about doing next? And they looked at me a bit askance and said, don't really want to tell you that. And I said, well, why? I'll happily tell you exactly what I'm going to do. And I proceeded to describe what I was going to do. And they said something that I hadn't thought about. They said, that's easy for you to say because we can't do what you can do, because you have infrastructure that we do not. If we tell you what we're going to do, you can send a grad student off to replicate that quickly because you have the tools to do that. We can't replicate the experiments at scale that you can do. And I realized that that was in fact true because I'm an experimentalist. That unique infrastructure creates competitive advantage. If you have tools that someone else doesn't, you can ask and answer questions that they cannot. And that's led to a lot of the competition in science around instrumentation. What's interesting about this switch to the broad availability of large-scale data is that it turns some of that on its head. Because the truth was that young assistant professor might have been asking better questions than the ones I was asking. But they couldn't actually go find the answers. Whereas I could ask questions that they couldn't, and they might or might not be as good at questions. But when things are turned on their head, suddenly advantage accrues to the person who can ask the better questions, not who has the better infrastructure. And that's an interesting social shift that we're starting to see in parts of science. And it speaks to some of these broad competitions. So this is a slide from my old friend Tony Hay, who used to be a researcher in the UK and now was one of my peers at Microsoft Research. And he was trying to make the point that if you think about the history of science, that pre-experimental method was largely descriptive. And we codify this notion of the big lie we tell students about the experimental method, about hypothesis and theory and experiment. And we moved, over time as mathematics improved, and I'm looking at John Rice here thinking about numerical analysis, as we moved to a world where we could balance theory and experiment with computing, we were able to bring a lot of those theoretical models to computational life. As computational simulation and the power of those supercomputers lets you ask questions that you can neither ask experimentally nor theoretically. Because although you may be able to derive the equations, you can't deduce all the subtleties that they may infer, particularly when they don't have closed-form solutions. And certainly some of the experiments aren't possible. I relate a story about the limitations of computing. When I was an undergraduate, there was a fellow who was doing computational models of stellar evolution, was looking at the burning shells of a transition from hydrogen to helium as they burned up to iron shells. And he was running this long-term simulation that was just bringing the computer center to its knees, and it ran for months and months and months. And the computer center operators are getting kind of annoyed and finally said, "When are you going to be done?" And this is this guy's PhD thesis. And so I finally went back and looked really carefully at the model and discovered that yes, the model was correct and it was evolving appropriately, but it was evolving slower than real time, which meant that it could be a couple more billion years before the model finished. And the computer center operator said that probably wasn't a good bet. Certainly his thesis advisor said probably not going to graduate with that. So, but you can do experiments that economics or physical realities otherwise constrain. But this emergence of big data has really brought some transformative effects. And so it's been called in many circles the fourth paradigm to complement theory, experiment, and the third one being computational modeling. But as I said, this really has had a psychological shift in many domains, from the hypothesis-driven, I have an idea, let me go test it, to what can I glean from the data. Now there's always a risk here about data analysis, and anybody who's worked in machine learning has heard this canard hoisted, which is correlation and causation. They're not the same thing. Things can be correlated but not causal. And so there are risks that just because you see correlations doesn't mean that they are predictive. And that's always one of the challenges of data analysis. But nevertheless, a huge set of opportunities to come from that. But I will say that all of us are facing a big challenge in this world. And let me I actually speak for a living. Speak specifically to one challenge, which is we face in research a big issue, which is the cost of producing and maintaining data is putting increasing attention and tension on our ability to fund people to do research. The cost of instrumentation and the cost of storage processing is skyrocketing. Now you may say, how can that be true given what I just said about the exponential decrease in storage costs? Remember, the free storage is a lot like being given a free puppy. The puppy is the cheap part. It's what happens after you get the puppy that's the expensive part. The chewed furniture, the mess on the rugs, all the other stuff that go with that. The cost of data acquisition is the cheap part. The real expensive part is maintaining it and analyzing it after the long periods of time that are often required. One of the other things that I want to sort of come back to circle up and close on is increasingly the value of big data accrues in correlating it across often divergent disciplines. And that means that we have to make it accessible to different groups. And that's a big, big issue as well. Here are some other things to think about. I spent most of the last 5 years traveling around the world talking to government leaders about the effects of technological change. And what I want you to think about is this, and I want to cite a few examples of it. Historically, the effect of technology change was felt on a generational basis. Those of us who are balding or gray-haired, if we think about our parents, the skills they had at 20 mostly served them their entire lifetime. That's no longer true. Regardless of the high quality of Purdue education, it'll get you your first job, your second job, maybe your third job. It will not get you your 8th job. And you will almost certainly have 8 jobs before your professional career is over. The question is, how do we deal with these huge cultural disruptions that occur when entire economic strata are destroyed on a time scale of 2 to 5 years? That's a huge issue. The rate of these exponential changes are affecting the linear ability of us to adapt, because all these technologies are changing on an exponential scale. We tend to deal in things socially in a much more linear way. There are big, big issues around that. Here's one to think about. Think about privacy. Almost everything that we believe philosophically, ethically, and legally about privacy, at least those of us who come from a U.S. background, is derived from English common law. Your home is your castle. Your person is private, right? Those are fundamental concepts that we all hold true. Those are physical ideas, right? They relate to a place and to your physical person. What's the analog of that in a digital world, where your digital persona travels across the planet in milliseconds? And you may think that's just an abstract question, but I'll pose a question that I posed to Penn Law School faculty a few months ago, in the fine sort of, here's a question with no answer that you should write a law school exam question about. And it goes something like this, and you can change the countries and the names, but the question is fundamentally the same. I said, you're a Kenyan national. You work for a German company. The data for your company is stored in Ireland, in this case a Microsoft data center. You get on a plane with your mobile devices, you change plane in New York on your way to Beijing. Whose laws apply to you and your data? Widely different cultures, widely different legal perspectives, and the answer is all of those and none of those in some interesting way. But this issue of global movement of data and individuals is very real, and it brings into conflict some very different cultural norms. And how we reconcile those is more than an abstract question. It's a very real one. As much as you may swear at all of those pop-up dialogues every time you go to a web service and it says, do you consent to this 97-page document before you use this service? How many of you actually read those things? That's what I thought. You are at least asked. Now, you may have to be a lawyer to understand them, and you may not have the patience to do it, and it is a bit of a Hobson's choice, because the answer is click yes and use it, or no and you can't. Not much of a choice, but you do have a choice. It is possible to stay off the web. It may not be very attractive these days, but it is possible. There's a very real social and technical question behind that, and it's the following. You can't ask people that question too often because they'll be annoyed and they won't use your services. Microsoft has experienced that. Every company in this space has experienced it. There's some social dynamics there about how often you can ask certain questions. And people struggle to figure out what that balance is. But at least there is an ability to ask. As we see the rise of more and more passive data, because when you click yes, you are making a choice. If you think about the rise of passive data with ubiquitous sensors, security cameras, and other things, you are leaking gigabytes of digital data every time you walk down the street. Your cell phone is tracking you, toll roads are tracking you with cameras, there are sensors all kinds of places. Who controls your digital persona in that world where there really isn't any concept of query and consent? It's a passive capture of data. It's a social issue unresolved, but it's a question about the rise of big data. So here's the thing to think about, and I just want to leave you with a couple thoughts around this. Whether you think Toffler was a prophet or just a bookseller, he did talk about some of the things that I've mentioned. You know, the waves that have affected society. So the first wave of when we moved from being hunter-gatherers to an agrarian society, to what we saw with mass production and the cultural changes that occurred with the Industrial Revolution. And the sort of post-industrial wave now, where we've seen some big social changes because of technology. What are these issues about how we affect change in a consensual way? And one of the big debates that's raging right now is the following, related to the effects of automation. Think about what's happened since the economic downturn. Most major companies are sitting on massive amounts of cash. Right? Some of them are investing that cash, but they're sitting on lots of cash, and there's because there's lots of economic uncertainty there. But if you look at what the effects of automation is doing, the production efficiency of many, many companies continues to rise, and therefore they're able to sell product. What they're not doing is creating jobs. Now they're making rational economic choices. Absolutely, I'm not criticizing the companies. But there's this question sociologically about what we do to create effective jobs for new generations when technological automation is creating some big shifts. And I say all of this to say, particularly to those of you who are students, that when you get fixated on the technology, it's important and absolutely critical that you be facile with the technology. But it's really important to think about the social context in which the technology is used and applied. And as you talk across cultures, and I don't just mean the human kind of culture, but if you talk across technology, across business, across public policy, what you almost always find is there is no lingua franca. There is no common dialogue. There is no shared understanding. People talk past one another because they don't understand the implications and the constraints of each of the groups. What can be done technically? What is politically constrained, what is economically constrained, what is socially constrained. Those are really, really important things. It affects us in the university world. This is sort of the last thing I want to leave you with. We in the university world, and I'm now back in it, have a great temptation to believe that, and this is not a religious comment, that the current structure of the university was brought down on a secret third tablet by Moses. In point of fact, at least the public research university has changed dramatically over the last 150 years, right? I mean, think about where I started, about the Civil Rights Act of 1964. Higher education in this country was created mostly to educate clergy, and you had to be landed gentry to be eligible to enter that, right? That's why Harvard was created, was to educate clergy. What we've seen over the last 200 years has been the increasing democratization of access to education. The land grants, the Civil War that created a land grant institution, so which Purdue is a great example, did that. Everyone has been about this democratization of access, and certainly modern science as we know it is a post-World War II creation. Come on in. In conclusion, there's no reason to believe that the university of the future will look like the university of the past. And we all know what this dynamic over here on the right. Everyone who's a parent or has seen a backlash about rising tuition and declining state funding for public institutions knows about this. Those of us who are in the research business know that funding for research is flat and not likely to change. And if you want to think about the social reality of U.S. federal funding for research, remember that the U.S. government is a social service organization that has an enforcement arm, i.e. the U.S. military, and some hobbies. And everything we're talking about is in the hobbies category. So the world, I think, will change, and it's going to hinge on thinking about these broad issues. And this really is the last thing I want to leave you with. Computing over the last 50 years has gone from being a niche thing to a major economic force. There are lots of U.S. studies that say well over 30% of net economic growth over the last 30 years has been due to information technology. We're a major force in society, in these cultural issues, and economically and scientifically. That's why I talked about computing and science, computing and data, and these social problems, as well as the economic and educational ones. And there's a huge debate, of course, raging now about online, massively online courses and what that means for the future of higher education. But we're a major force. But one consequence that's happened because of that is when you're a mouse scurrying among the big beasts, you worry about not being trampled on. And that was historically what computing was. When you're a big beast, the hunters go after you. And as computing has become big science, it is in the cultural crosshairs in a way that it has never been before. And that's why it's important for us to think about how we engage in these issues. Because if you go talk about research funding and the future of computing, and you say, this is a cool idea, I'll tell you a story about that. Served on a bunch of presidential advisory committees looking at computing and science, and on one of them, I went to talk to the Office of Management and Budget and about the funding process for computing. And the OMB examiner looked at me and he said, you know, I realize this may or may not come as a surprise to you, but very few people come to Washington and say, I am dumb and I have too much money. Can you help me fix my problem? Most of the time, there are more good ideas than there are resources. I mean, that's the conundrum, that's why they're choices. So how we think about actually helping address real societal problems is one of our challenges and opportunities. And I'll leave you to think about a couple. Think about the challenges we face socially around the rising cost of health care and the yet unfulfilled promise of personalized medicine as part of the post-genetics human genome revolution. We haven't fully capitalized on that. One, because it's a lot more complicated than we thought. I have a cartoon I sometimes use in talks that shows the computing view of biology. And it shows this massive crossword puzzle pile. There must be hundreds of millions of pieces heaped up on the table in its computing approach to biology, and the caption says, I've made progress. I found a corner piece. It's a little harder than that. But how we think about applying technology to realize that promise, but to lower healthcare costs, those are real societal and economic issues. You know, how we think about advanced manufacturing, some of the issues about the future of additive manufacturing as opposed to subtractive manufacturing, there are huge issues around that. And there are a huge, huge set of issues around the future of intelligent transportation and smart cities. Everything from autonomous and semi-autonomous vehicles to what true smart grids actually mean. And I'll leave you with one final punchline around that. A few months ago, I was talking to the Danish environmental minister. And Denmark was in the midst of deciding what fraction it would legally commit to of its national energy budget to be renewable. And the hope was 100, and they finally compromised at around 50%. But the question we were debating was, what is the future of smart grids? And I told him a story about another meeting I had attended not long before that, which was a meeting with a group of computing people and a group of folks who built and operated electrical utilities. And the question posed to the group was, what's the future of smart grids 30 years in the future? And the whole idea, of course, is if you have real-time data, you can use that to manage loads and mix renewables and non-renewables, and you can adapt dynamically. There are a bunch of privacy issues around that, which are a talk for another day. And so the question is, what could this look like 30 years in the future? And me, perhaps being an unduly difficult person, I raised my hand and I said, I have a question. Okay, what's the question? I said, 30 years in the computing business, you're asking me to tell you a science fiction story. Because I don't know what 30 years looks like. 5 years, I could give you a pretty good guess. 10, you know, something credible. Anything beyond that, you might as well ask David Bren to come talk to you as to listen to me. And the utilities folks said, well, that's really too bad. And I said, why? And he said, because from our perspective, 30 years is tomorrow afternoon. And it really is, because if you think about the amortization schedule for a large-scale utility, that's about what it is. So there's a cultural gap there. And part of what I'm really saying for all of us in computing, as we think about these big changes, what's important is that we understand where the rest of the world is, culturally and politically and sociologically, and understand how to bridge that gap. That's why before I was saying there really is a difference between sashimi and dead tuna. The sashimi is the story you tell to people that they understand in their world. The dead tuna is the technology. And you've got to make that bridge work if you want to make things happen. And I've talked too long already, so let me stop here and thank you.